Right, on chemical equilibrium. This is just the notes. What will be covered for chemical equilibrium. Right, firstly on the chemical equilibrium, Parasonjo observe these following definitions. But strictly 1, 2, 3, and this one. So under the equilibrium, what do you call a closed system? Now, as you must understand what is a closed system. We have a closed and open system. Now, having a container like this and having the chemical reactions taking place and maybe some gas going out. Namely, this one we call it an open system. And then what is an open system? It's a system where a reaction interacts with its surrounding on the environment. That's an open system. But we can have a closed system where now we can put a lid on this one and then have a chemical reaction taking place in here. So there is nothing escaping in here. Was running titlono kira modima ali to legend then jabuela inside the container. So this means it's a closed system. Now a closed system is a system where the reaction is isolated to interact with its surroundings. So interact the surroundings of inside this container. This is a closed system. So meaning if it's a closed system, if the reaction near here, or this reaction regard IAM, but this one at the end it will because the gas IPC escape, but some of the reactions but come in a closed system, this reaction because it will not continue up products to the reactants. Products will turn back to the reactants. That is what is happening in a closed system, and then that's why we have the term reversible reaction is only happening under a closed system. So reversible reaction or the reactants, and then they'll form products. And then now we're going to have the products being converted back to the reactants. Now, if that is the situation, it means rather it must be a closed system, and then after having closed system, then that's when you can have this products that fit this as long as this is not collect, then they can turn back to the reactants, and then rather this system it will not keep on circulating throughout. It will just circulate throughout like this. So it will circulate reach the different equilibriums, so to continue doing like this like a cycle. That's what we mean by a reversible reaction. So meaning that reactants can be converted to product and the products can be converted back to the reactants. That is a reaction by where the reactants are converted to the product and the product can also be converted to the reactants. Then that is what we call a reversible reaction. Right, the chemical equilibrium or the dynamic equilibrium. In the other name for chemical equilibrium, they say dynamic equilibrium. Now this one we'll say is a dynamic equilibrium where the rate of the rate of the forward direction is equals to the rate of the reverse direction, or the rate of the producing the products is the same as the rate of producing taking the products to the reactants. But the proper definition is when is a dynamic equilibrium when the forward direction is equals to the rate of the reverse direction. So you can go to exam guideline and copy the exact definition. Right, the dynamic, I think it has to do with the movement. The movements, that's what we mean by dynamic. That's why here dynamic equilibrium, the rate of something is produced is moving to the right is the same as the rate of something moving to the left. Right, the Le Chatelier's principle is just a principle where we are going to disturb this the production of the products and the production of the reactions, where we call it somewhere they reach equilibrium. So this Le Chatelier's principle, they're saying if a disturbance is being made this side is being made on the reactants, so rather we can, if we make a disturbance here, now this system will shift away from this disturbance. System so it depends on the disturbance, and then this disturbance the system will just run away from. If for the system will shift, okay, let's say we're going to do a disturbance in here. So the disturbance in here that we do, we can do two disturbances on the reactants. We can have addition of the reactants and the removal of the reactants. So this one on the removal of reactants, then if we remove, then system will shift back to the other part here. So the system will shift to cancel whatever disturbance that is being done in here. So meaning if we make a disturbance on the other side, then the system will need to shift to cancel that disturbance that is being made, so that everything will still balance. Because when we disturb the equilibrium, it means the rate of this forward direction will be the same as the rate of the forward reverse direction. So in this case, we're forward, and then let's set it over a reverse direction. So forward and the reverse direction. So when I say system is equilibrium, it means the rate of doing this is that's the same. Because when you start the reaction, normally we have the reactions. And then they will go at higher rate producing the products. And then it means by this time, when the reactions are just starting to do the products, now the reverse reaction will be very low. They will not be the same. So because we started by the products producing the reactants, now the rate at which the products are converted back to the reactants is very small. But as time goes by, then we're going to have this the rate of the reactants being equal Here will be the products. So what we're going to have, the reactions are produced, are used to do the products, and the products are also being taken back. But we have a time where reaction, the rate of this forward direction, the rate of this reverse direction are equal. Then when they are equal, then that's when you say the rate of forward direction and the reverse direction are equal. It means this when they are is like this, it means they are at equilibrium. So both rates are equal. Then having them like this rolling, we can now do a disturbance while they are equal, or the rate as which the products are made is the same as the rate where the products are converted back to directions. Then if we do, that's when we can do the disturbance here. The disturbance, maybe we want to favor the forward, or we want to favor the reverse. Then this is what the Chastel's principle say, that if we do a disturbance while the system is at equilibrium here, then the system will just shift to re-establish that disturbance, to cancel that disturbance that is being made. So meaning if we add this side, so there will be more of these reactions. Now it's no longer balancing the rate of with this one. Then it means when we add here, the system will just shift to the right, and then it means in favor the forward direction. Then it means if we remove here, then there will be a shortage in here, and there will be some other more products in here. And remember, these are converted back to direction. Roaring system is when you shift kapela or to cancel that disturbance dealing of directions. Then it means the system, in this case, will shift to the left. So that's what the principle says. But check the proper definition. Here is just an application. We'll do more application down there. Right, after knowing this parts, they are saying list 3 factors that affect equilibrium position. Now we talked about equilibrium position where the forward direction and the reverse direction are equal in rate. So this when they're equal, what disturbance that we can do? We can do with these 3 factors. Can change these factors to affect the equilibrium position. So the factor number 1, you can change the temperature, you can change the concentration, you can change pressure. These are the 3 factors that we can change to affect the position of the equilibrium. Name the only factor that can change the value of the equilibrium constant. Now we also have what we call equilibrium constant called a Kc. Now we'll get in details of that, but for now let's just know that the Kc value, which is the equilibrium constant, it can be affected, that value of Kc can be affected by the temperature only. So they say only in bold. So writing, if whatever they say, they change the concentration, they change whatever, and what will be the value, the value of the equilibrium constant, that will remain the same until the temperature was a factor and it was changed, whether increased or decreased. Then it means the value of Kc will change. But these two, concentration and pressure, they change the value of Kc. They not change only the position. It will because when you do the affect, will do the disturbance. While in the equilibrium, will need to shift. But if it also do temperature, then you also affect the value of the Kc. Take note of this. Right, conditions for chemical equilibrium to occur. Now, this is some important conditions. For equilibrium to occur, we must have a reaction that is reversible. So Note number one, we must have a reversible reaction. Number two, the reaction must take place in a closed system. Condition number two, we have a closed system condition. If there's a chemical, we need a chemical equilibrium to occur. So if there is no closed system, there is no equilibrium. If there is no reversible reaction, there is no equilibrium. Meaning that the system must be closed and reversible. There is a forward and a reverse reaction in a reversible reaction, and it is indicated by a double arrow. So it's indicated by, we use this one to show the forward and the reverse reaction. So but they can even use this, fine, but normally we'll get used to this one to show that it's a reversible. So if you check a reaction, maybe even if it's not balanced, we can have H2 plus N2 to produce, being a reversible reaction, and H3. For the fact that they used these arrows, it means it's a reversible reaction. But remember that with chemical equilibrium, the concentration is a quantity that will be considered. And then they say, so solid, shown by a subscript S, and pure liquid substances will be ignored. Only aqueous gas and gases will be involved in this application. Let's read it again. Remember that the chemical equilibrium, the concentration is the quantity that will be considered. So if now we have a solid, liquid substances will be the equilibrium concentration. So remember the concentration, we want to check the square brackets. So if you see something, a compound by the square bracket, it means that is a concentration of that compound. So solid S and pure substance, so the global ignored. This will be the subscript. So in other words, what are these? P means S and L, liquids, are the phases. The phase at which a compound appears. Only aqueous. So if you wanna a molecule bangala G, they will be involved in this application. So we'll explain that in details. Right. They are saying when explaining using Lechausseux's principle, use the following key sentences for guaranteed marks. So we must use these following sentences for guaranteed marks. If forward direction is favored, the concentration of reactions will decrease and the concentration of the product will decrease. Now they say if we are using Lechausseux's principle, then we must use the following. They say if the forward direction is favored, the concentration of reactants will decrease and the concentration of the products will increase. Right, this is what I was trying to explain. They say if the forward direction is favored, the concentration of the reactants will decrease and the product will increase. So we had this one, and H3. So they say if a forward direction, what is a forward direction here? So the forward direction will be this one. So if the forward direction is favored, it means more the higher rate of friction will come this side. So meaning a lot of things are being taken from this side to the other side. So it means the concentration in here, the concentration of this reactants will decrease. They will decrease. While recharge winchiwa number of molecules kamore kamo. Then what it means now the then roaring the concentration in here will increase. So whatever that is in here will increase in concentration. Whatever that is in here will decrease in concentration because of the forward direction is favored. Then if the reverse direction is favored, then the concentration of the reactants will decrease. The concentration of the reactants will increase, yes, not decrease, it will increase. Or if reverse reaction is favored, it means this time running favor this reaction that is driving that way. So in this way. So what is that side roaring? We're going to take a lot of the moles in here. So roaring too much the amount in here will increase and then the amount in here will decrease. So that is what we say when we are using the Lechatelier's principle. Now the table on the next page summarizes the answer. So this is how we should give. This was just explanation to understand, but we must give the following the exact way as the table summarizes on each factor is affecting the equilibrium. Let's check next page. Right, this is exactly what we're going to say. Now what we're going to do spot our factor if factor it change more. So now if the factor is a temperature, temperature can be increased or decreased. So if it's increased, this is what we're going to say. We're going to say the system favors direction that will decrease the temperature, right? Okay, but in fact your answer will start here. Increase in temperature favors the endothermic reaction. Full stop, then you get a tick. Just say an increase in temperature favors the endothermic reaction. Then here they are saying mention which reaction is favored, forward or reverse. Now here that's why you need to be careful. Which one is favored here in terms of endo and exo. So having a reaction like N2 plus H2 is equal NH3. Now if we have it like this, less than 0, then we can see that the temperature is increased. Then now what does this sign mean? So this sign simply means here, it means what is this part here is saying delta H is less than 0. We did this in rate of fractions, so meaning that this represent an exothermic reaction. Now if this is an exothermic reaction, then what we have, what does it mean? It means this school system may be more the forward reaction. Always shows the forward. And then if that is the case, we have forward here. It means the one that is going back, it means which is the reverse. Reverse is endothermic. So this one always represent a forward direction, and it means the reverse direction will be the opposite. Then because we are given that the forward direction is an exothermic, then the reverse direction is endothermic direction. But that's why they are saying mention which reaction is favored, forward or reverse. We increase the temperature, then according to this one, we know that an increase in temperature favors an endothermic reaction. Which one is an endothermic reaction on this reaction here? So our endothermic reaction is the reverse reaction. Then we're going to say a reverse reaction is favored. Then we get another tick for just recognizing which one is favored. Now they say mention the change in concentration of the reactions and the products. Now we'll try to explain. Now because the reverse reaction is favored, it means we're going to say the concentration of the reactants, because we need a change. So the concentration of the reactants, what is happening? Running, because the system running towards the reactants, then it means the concentration of the reactants increases, and the concentration of the products decreases. That is what we're going to say. Then after saying that, you're going to get showing that. So normally that will be your 3 marks on how to reason when this is done. Then if that is the case in here, we're still given a situation, if there is a decrease in temperature, the system favors the reaction that will increase the temperature in here. So, but the saying decrease in temperature favors an exothermic reaction. Always that is the case, and you get a tick. Then the next one, they say mention which reaction is favored, and then in terms of this case, if the forward reaction is exothermic, then we're going to say the forward reaction is favored. We're going to say the forward direction is favored, not this one. And then you get another tick. Mention the change in concentration. Of course, if the forward direction is favored, it means the concentration of the reactants will decrease and the concentration of the products will increase. That is what we do in temperature. Let's check the factor number 2, which is pressure. Now, if we're talking of pressure, and when we're saying pressure, it must affect only gas. It must only affect the gases. So if a pressure is increased by decreasing the volume of a container, now pressure and volume, they have an inverse relationship, knowing that pressure is inversely proportional to the volume. So we can increase pressure by decreasing the volume of the container. So meaning we showed an example, if the volume is up to here, then we have this rubber stop here. Then if you compress this down there, we're decreasing the volume, but the particles that are being here, they'll be exerted, they'll experience more pressure. Then that's what we can say, volume and pressure, they are inversely proportional to each other. They have a relationship. Right, they say increase in pressure. The system favors direction that will decrease the pressure. Will favors direction that will decrease the pressure. So if you increase the pressure, the system will favor, it will decrease pressure. Because re gatela one side, or system on the other side of the product or reactions, or modeling, it will experience a less or a pressure, which is decreasing pressure. But this is where you start to answer. They say increasing pressure favors direction that proceeds towards fewer number of moles. Will favor a direction that proceeds to fewer number of moles. Or if you get pressure, system less number of moles. Let's have a balanced reaction. H2 plus N2, it will produce NH3. Now let's try to balance this one. So we have two nitrogens. Now they are 2 balanced. We have 6 hydrogen, 2 by 3, 6. Then we need to put 3 here. Now this is what we have, is balanced. Now let's check what is the total number of moles. When we check the number of moles in this case, when we say the number of moles in this case, we check the ratio. So 1. So what is the total number of the ratio? This side, which is called number of moles, is 4. This side is 2. So they say increasing pressure favors this one is just a statement. Make sure that you write that statement if there's increasing pressure. So this statement must be there. You get a tick for that. Then it comes where we say mention the direction that is favored. How do you know which one is favored? Now we increase the pressure, and we say the increase in pressure will favor the direction that proceeds to fewer number of moles. Which one is having fewer number of moles? Is this one here, 2. Right now our system will favor the forward reaction, will jump to this side. So meaning this side will say forward direction, forward direction is favored. Mention the change in concentration. Now we need to know the change in concentration of the reactants and the products. What we're going to say, then it means if it's available, then of course the reaction, the concentration of the reactants will decrease and the concentration of the product will increase. That's what we have. Then the other part will happen again opposite on the if pressure decreased. Now let's check the concentration. Now, if the factor is the concentration of reactants is increased. Now, they said the system favors the reaction that will decrease that reactants concentration. So that if we increase the concentration, system it will chabela ka mo loreng it will decrease the reactants concentration. Now, in this case, let's make it clear. They are saying for the system favors the reaction that will decrease that reactants concentration. So right, we're going to check which is that system. Forward reaction is favored, concentration of reactants will decrease and the concentration of the products will increase. That's when if we increase the concentration. So it doesn't matter which side, but when we talk of concentration of the real, here they stated that normally we increase the concentration of the reactants, not of the product, but we're talking of the concentration of the reactants. So already if the reactants is increased, then the system favors the reaction that will decrease that reactants concentration. So obviously when we add the concentration of the products or of the reactants, so the system will shift, because if we have N2 plus H2 like this one produce NH3. So of course if we add the concentration this side, this concentration is being added, so the system obviously will shift to the right to decrease the addition in here. So addition to balance the two, or I apply kind of Lich's principle to balance the two. So that the concentration of this one must increase, because they're saying it will decrease the so the favor side to decrease at this concentration that is being added here, which is the fourth. We can only decrease when reach on the other side. Then it means the forward direction is favored. That is always the case. Concentration of directions, then these two statements are always like that. So this one, if it's concentration, everything you just write it like this. You copy this statement. You must just memorize that one or understand it. And the same will happen on the decrease in concentration. So here is if a concentration of the product is increased. Now this one we're talking of a product. So we need to be careful which one is increased. Is it the product or the reactants? Now the system will favor the reaction that will decrease the product's concentration. So this one you just copy as it is. Then in this case, if we increase the concentration on the products, obviously the reverse reaction must be favored. Then the concentration of the reactants will increase and the concentration of the product will decrease. So this statement of concentration, they are given exactly. Running how to modify, you just write as they are. Running when I was to be careful, right? But which concentration by adding? Let's say if we have N2 plus H2 NH3. So meaning in this case, every concentration of the product, or if the concentration on here of sodium, which means it's an ammonia, of this ammonia, then if they say the concentration is increased, obviously is on the product side. So the system will shift to the left to decrease this concentration of the product in here. That is what they are saying. Then it means the reverse reaction is favored, because it will jump to the left hand side to favor the reactants. Right, remember that the Kc value can only change if the temperature changes. So this is what you need to take note. Use the following expression or equation to determine whether Kc value will increase or decrease. Right, the Kc value is the concentration of the products. This is the concentration. Concentration of products and the concentration divided by the concentration of the reactants. Now, this is the reactants, or the concentration this side and the product this side, then are on this one. So due to the change in temperature, Kc value increases if forward direction is favored. Now, if we favor a forward direction like this, then Kc value, it means will increase. Why? The concentration of this product will increase, and this one, the concentration of this one, of course, will be decreased. So by a bigger value. That's why we're going to have a Kc value increased. Kc value will decrease if reverse reaction is favored. Why? Because we have an increase in the reactants, so we're dividing by a bigger number, whilst the products they are decreasing. So that's what we have on the Kc. So meaning increased here, meaning Kc will be greater than 1. But here Kc will be less than 1. So if you are doing a decrease there, which is favored, this one is the reaction is favored. So but remember Kc is greater than 0, greater or equals to 0, cannot be negative, so it's always positive. But that will be the first part. Now we come to the interpretation of the graphs on the next lesson.